Welcome, students, to this explainer on Chapter 9.3 Software Maintenance in our overall Chapter 9 summary. This is a totally critical and, quite frankly, often overlooked phase in your software engineering journey. So often we get caught up in the thrill of creating something brand new, but today we're going to look at the reality of what happens next. Consider this a masterclass in the long-term survival of the software you build.
Okay, here's our quick roadmap for today. We'll start with an introduction, look at the types of maintenance, dive into why the costs are so high, explore re-engineering and refactoring, and finally, wrap up with a chapter summary and a clear exam focus.
All right, let's jump right into Section 1, Introduction to Software Maintenance. Let's start by breaking a very common myth. Software development absolutely does not end the moment the product ships. I want you to ask yourself a really fundamental question. What actually happens to a software program after it's delivered to the customer? You might think, well, we pop the champagne and move on to the next project, right? Actually, no. Businesses change, and users, well, they will always find creative ways to break things you literally never anticipated. Deployment is really just the beginning.
And that brings us to our formal definition. Software maintenance is the general process of changing a custom system after it has been delivered. Now, I really want to emphasize that word custom here. When a company pays for custom software, you usually have totally separate development groups involved before and after delivery. And here's the sobering truth, students. For custom software, these post-delivery maintenance costs usually completely dwarf the original development costs. You're going to spend far more time and money maintaining a system than you ever did building the thing.
Moving on to Section 2, the 3 types of software maintenance. Since post-delivery changes are just a fact of life, we need to categorize exactly what we're doing when we maintain a program. And the reality is pretty surprising. Maintenance isn't mostly about fixing broken code. Fault repair, which means fixing coding, design, or requirements bugs, that only accounts for about 24% of the effort. Then there's environmental adaptation, taking up 19%. This is when you're updating the software to work on a new operating system, a different hardware platform, or a new database. But the massive slice of the pie, sitting at a whopping 58%, is functionality addition. Adding entirely new features to meet changing business requirements is, surprisingly, the most common and absolute most expensive type of maintenance we do.
Which brings us perfectly to Section 3, the high cost of maintenance.
Since adding functionality clearly dominates our time, we really have to ask, why are these maintenance phases notoriously expensive? Well, it boils down to a few core issues. First up, after a system is delivered, the original team is usually broken up. A completely new team takes over, which means they literally have to spend weeks just reading and understanding the existing program before they can safely write a single line of code. Second, there's a huge lack of incentive. If developers know a different company is going to handle the maintenance contract, they have zero incentive to spend extra time writing clean, easily maintainable code. Third, maintenance just has a poor image. It's often viewed as unpopular work, cleaning up someone else's digital spaghetti, so it sometimes gets handed to the least experienced staff. And finally, as a system ages and changes are hastily patched in over time, its internal structure just naturally degrades.
Let's look at how we handle this in Section 4, Predicting Maintenance and Reengineering.
So with these massive cost drivers and code that's slowly rotting away, how do we predict and fix these programs before they just completely fail? Well, we predict maintainability by asking some very precise questions about system degradation. Before we even touch a legacy system, we assess it. We ask, how difficult is it to understand the source code? Is the documentation complete? Or, hey, does it even exist at all? Is the programming language completely obsolete? By asking these specific questions, we can accurately pinpoint which parts of the program will be the most expensive to maintain and budget accordingly.
Now, when a legacy system is highly degraded but it still provides vital business value, we turn to software re-engineering. This is defined as a major overhaul of an old, degraded legacy system to improve its structure and understandability, crucially, without changing its functionality. Think of it like this. It's like stripping a house right down to its foundation and rebuilding the walls without changing the actual floor plan. It's a massive undertaking, absolutely, but it's significantly cheaper and way less risky than scrapping the whole system and starting entirely from scratch.
Let's walk through how this builds sequentially, using the textbook steps of the re-engineering process. First, we have source code translation. This is like converting obsolete code into modern Java or C++. Second is reverse engineering, where we analyze the program to extract lost documentation. Third, program structure improvement, where we modify the control structure to make it readable again. Fourth is a really crucial term you need to know,
Program modularization. This is where we group related parts of the program together and remove redundancies to create a cleaner architecture. And finally, data reengineering, which involves cleaning up and restructuring the underlying databases.
Now, depending on the state of the program, you might not actually need all of those steps. There's a whole spectrum of reengineering approaches and associated costs. On one end, automated source code conversion is relatively cheap. But as you move towards full program and data restructuring, the costs increase exponentially. Major architectural changes simply can't be automated, making them highly expensive manual processes.
All right, let's pivot to Section 5, Refactoring and Real-World Application.
So reengineering is a massive, reactive overhaul used when a system is already failing. But what if we want to prevent the system from getting to that state in the first place? This brings us to refactoring. Refactoring is continuous, preventative maintenance. It's the process of making small, incremental improvements to the code structure without adding any new functionality. In the industry, we often call this fixing bad smells, like removing duplicate code or breaking down a massive, confusing method into smaller, much more readable chunks. Agile methods rely heavily on this constant tweaking to prevent that structural degradation we discussed earlier.
So the absolutely crucial point here is distinguishing these two concepts for your exams. Software reengineering is a massive rescue operation. It happens as a distinct phase late in a product's life when maintenance costs are just spiraling out of control. Refactoring, on the other hand, is daily hygiene. It's continuous, integrated right into the daily development process, especially in Agile, to ensure the code never degrades to the point of actually needing a rescue operation.
Let's apply this to the real world. Imagine you're responsible for maintaining a massive registration system for a large private higher education institution right here in Gauteng. This system handles thousands of students, module selections, and financial records. If your team uses continuous refactoring every single sprint, cleaning up the database calls, simplifying the registration logic, you keep the system healthy. If you don't, well, over 10 years, that system's behavior will become so unpredictable and slow that you'll be forced to spend millions on a massive reengineering project just to keep the institution running. Daily hygiene literally saves millions.
Let's wrap things up with Section 6, Chapter 9 Summary and Exam Focus.
Keeping that Gauteng registration system in mind, you can clearly see why understanding how software evolves is just as important as knowing how to build it. Looking back at the overarching themes of Chapter 9, remember the distinction between evolution and servicing. Evolution is the active spiral model where we make significant architectural changes, while servicing is that late-stage phase of making only minor essential fixes before retirement. We also covered legacy systems, recognizing them not just as old code, but as complex socio-technical systems that include obsolete hardware and outdated business processes. And remember how we evaluate them? We are always balancing their continued business value against their technical quality to decide if we should maintain, re-engineer, or scrap them.
Drilling down into today's specific masterclass, please anchor these concepts in your mind. We explored the 3 types of software maintenance: fault repair, environmental adaptation, and that massive cost of functionality addition. We unpacked software reengineering as the major reactive overhaul for degraded systems, and we contrasted it with refactoring, the continuous preventative maintenance that keeps our code clean day by day.
Now I want to be incredibly direct with you here. For your upcoming exams, mastering these specific items is mandatory. You must be able to list and explain the 3 types of software maintenance. Furthermore, you must be able to clearly explain the structural difference between re-engineering and refactoring and when each is appropriate in the software lifecycle. Seriously, do not script these definitions.
Congratulations on making it through Chapter 9 and mastering software evolution. As you move into the next phase of your software engineering journey, I want to leave you with a somewhat provocative thought. Every single time you write a line of code, you're making a decision for a developer 10 years in the future. So ask yourself, how will the maintainability of your code today impact the system dependability of tomorrow? Thank you so much for joining me in this explainer, and I will see you in the next lecture.